Good day, everyone, and welcome to our webcast, Methane Emissions from Wastewater Treatment. This webcast is the second in a series of 4 webcasts on the topic of wastewater process emissions. My name is Jeff Moeller, and I'm a research unit leader at the Water Research Foundation. And I'm going to go over just a few housekeeping items before handing off to our moderator today. In terms of housekeeping, you please submit questions through the question box at any time. We'll do a question and answer session at the end of the presentations. So keep the questions coming throughout the webcast. Slides and a recording of the webcast will be available at www.waterrf.org. Also, you can download the slides now under the event resources on the bottom left of your screen. A certificate of completion will be automatically generated after the webcast. If you have any questions about that, just feel free to contact Michelle Suazo at the email shown on your screen. And then also we encourage you to stay until the end to fill out a quick survey with your feedback. And now I'd like to hand it off to our moderator today, who is Jessica Akande, and she is a senior program advisor at the Canadian Water Network.
Thank you so much, Jeff. Hello, everyone. It's great to have you join us today. My name is Jessica Akande. Just like Jeff said, I am a senior program advisor with the Canadian Water Network, and I am thrilled today to be moderating this webinar on methane emissions from wastewater treatment. And so I'm just going to quickly talk about the agenda. Jeff has done a great job welcoming and doing the housekeeping rules. And so I'm going to moderate this particular webinar. Is the second, like Jeff said, would be John Willis, who will talk about how to measure wastewater methane. And right after John, Adrian is going to discuss direct measurements of methane. And right after Adrian, Trong will take over with the new bioenergy program, and we'll round off with a quick question and answer. And so before I get started with my introduction, the land acknowledgement is up here. At Canadian Water Network, we have a corporate goal of undertaking our Indigenous learning. And so you can read in that acknowledgement as we go along. But one of the things we have been taught is to actually speak from the heart. And so I am on my learning journey, but I am grateful, definitely very grateful, to have the opportunity to work in Waterloo, Ontario, which is about 1.5 hours away from Toronto, where CWN office is located on the traditional territories of Neutral, Anishinaabe, and Haudenosaunee peoples. And so this process emissions webinar series is brought together by a whole bunch of people, and those organizations are listed on the screen. And so it's organized by US Water Alliance and Canadian Water Network, graciously hosted by the Water Research Foundation, and presented in collaboration with the International Water Association, Water Environment Federation, and the Danish Water Technology Alliance. And so, the federal government of Canada has a goal of reaching net zero by 2050, but an interim goal of reducing greenhouse gas emissions by 40% to 45% below 2005 levels by 2030. CWN is a not-for-profit organization that facilitates knowledge mobilization and a space for deep collaboration between municipality and water utilities. And so we do this by tackling complex water-related challenges that affect our communities through our communities program, our health program, and our climate program, addressing resilience, adaptation, and mitigation. And so the goal of this webcast series has been to deepen understanding of GHGs from treatment processes. And so we hope through this webcast, we're talking about types and sources of GHGs, mechanisms and process conditions, quantification, measurement, and monitoring techniques, as well as emissions reduction strategies. And so just like we've said, this is the second webinar in a 4-part series. And so the first one took place on the fundamentals on July 19, and today is the one on methane emissions. And we have 2 more coming on nitrous oxide emissions on October 31st, as well as mitigation strategies on December 12th. And so if you were not able to attend the first one, this is a very quick recap. And so we had presentations by John Willis, Vice President Brown and Caldwell, who will also be presenting today, and Amanda Lake, Head of Carbon and Circular Economy at Jacobs. And it was moderated by Harry Zhang, who's the research program manager with WRF, as well as David Ponder, who was director of climate action U.S. Water Alliance. And so there were a few key takeaways. The first was that there is a need to daylight greenhouse gas emissions from water resource recovery facilities to create those additional opportunities needed for collaboration and funding. Another key takeaway was that for us to mitigate, we have to accurately measure greenhouse gas emissions through operational activities, but also do so in identifying all the sources of greenhouse gases within facilities. And as we go ahead today, you will hear about methane leaks and potential gaps that we haven't yet identified. Another key takeaway was as we reduce Scope 2 emissions by converting to other forms of energy, nitrous oxide and methane emissions are becoming more dominant across all the scopes of greenhouse gases, Scope 1, Scope 2, Scope 3. And finally, there are various factors that influence nitrous oxide and methane emissions, such as season, location, operational conditions, process type, equipment selection, and maintenance. And so without going too long, I'm going to pass it off. Our three presenters are on screen, but I'm going to pass it off right now to John Willis, Vice President Brown and Caldwell. So John.
Hey, thanks, Jessica. I hope that's coming through clear enough. Let me get organized on the slides. So my presentation is going to go back to where, actually, let me go through just quickly on the agenda. I'm going to talk through some of my early experience measuring methane, and this is through a number of old WRF projects. Go over quickly a list of possible methane sources that we brainstormed at Toronto when we were at IWA last month, and then go through a new project called the Greenhouse Gas Library, which was just given our notice to proceed last week, where we're looking at people, if you do measure your methane, to upload it to a repository where we can get researchers and scientists to take a look and develop them into methodologies. So starting off with my earlier methane measurement experience. So this is the first project, and it was a project that we did when Lauren Fillmore was our project manager. What I'm showing here are, I think, about 35 pumping stations in DeKalb County's collection system. A lot of them look exactly like the wet well on the left. They're constant speed pumps, and the pumps cycle on a high level on, and they drain the wet well, and then they stop. And what we did during this testing, and you'll see on the wet well that's on the insert in the middle, there are 3 different levels. There's a level at the top of the wet well, a level in the middle, and a level at the bottom. So what we would do was go to each one of these pumping stations in the winter and the summer and measure what the methane was at these 3 different elevations. We'd then average it. And then what we did is, as a function of temperature, we used a breathing method. So every time it fills, the wet well displaces a certain amount of gas. So we applied the average concentration to that volume. And then we looked at the number of times it cycled over the course of a year. And there were summer emissions and winter emissions. So what we ended up doing was estimating what the greenhouse gas emissions were for the year. And we ended up with a number that was 427 metric tons of carbon dioxide equivalent, which is not an enormous number. But when you think about all the methane that we were certainly losing during this, and the fact that we weren't looking at any other manholes, this is probably underreporting of what the methane actually was. The next example I'm going to talk about is some work that we did under another water research project. In this particular one, we teamed with the NASA Ames lab, which is based in Sunnyvale or San Jose, California. And what we did here was that we went to a plant, a large plant with a number of photosynthetic oxidation ponds. And what you're seeing is a number of EPA flux hoods in the facultative sludge lagoon A picture. But when you look at those 4 different pictures of the lagoons, you're seeing the sludge characteristics in each lagoon was different. In some cases, there was a lot of sludge near the surface. In other cases, it looks almost like a lake. And yet, if you look at the research and the data that we collected, you're seeing that the first one, FSL-A, emitted what's probably on the order of 10 to 12 times as much methane as either FSLB or FSLC. So when you look at the conclusions of this research, and I've copied them in here, what they basically said was that statistically, we believe the average emission rate was 3.6 grams per square meter per day for the facultative sludge lagoons. And interestingly enough, that was only half of the emissions that were measured at the Sunnyvale photosynthetic oxidation ponds. So the lagoons, while they've got heavy sludge in them that's already digested, are not producing, they're producing about half the methane. Now, when you look at those ranges, they're big. So for the facultative sludge lagoons, we were looking at less than 1 gram per square meter, up to almost 8 grams per square meter. So there was a big number there. Now, what I'm showing on the right is the 20 lagoons at this water resource recovery facility. And each one of these lagoons is about 7 acres large. So they're very big. And yet we're hoping to interpolate from these 4 sampling points what the emissions are over this entire area. So the final conclusion in this summary is important because it says, hey, we've done some basically grab sampling, and we really suggest that additional research be done in order to figure out, to refine this estimate and to figure out a better idea on what's actually going on. So now I'm going to pivot here, and this is to DC Water's greenhouse gas inventory that we originally developed in 2009 for calendar years 2007 and 2008. And I'd like to say I still think this is probably one of the most complete greenhouse gas inventories in our industry. I also want to acknowledge and thank a lot of folks at DC Water who made this possible. And currently, Chris Piot, Saul Kinter, James Fatui are still there. This was also driven to a large degree by Sudhir Murthy and Bill Brower, who are no longer at DC Water. Now, what DC Water wanted to do was to try and make their inventory as complete as possible. So that meant if we think methane or nitrous oxide is being produced by a process unit, let's measure it. And let's not just be beholden to methodologies and protocols that would allow us to take a good guess at what we're emitting. So instead, if they thought something was emitting methane, they would measure it. So what I'm going to talk about now is some of the measurements that we did. Actually, what I'm going to talk about now is all of the sources. So this is just a quick screenshot here of the electricity emissions. It's on the left-hand side. And on the right-hand side, those are all the scope 3 emissions that we put in the greenhouse gas inventory. Another point of note is that all of the green highlighted emissions were emissions that we collected new data for in 2017, 2018, when we were updating the inventory to add digestion-related emission sources, as well as emission sources that came into being when they implemented their denitrification sludge process, which dramatically increased the scope 1 emissions, in particular for anthropogenic CO2 from methanol use. So the next slide, these are all scope 1 emission sources. And you're going to see there are some numbers here that were planned. And we were envisioning, well, if they use ethanol in vehicles, then we'll include ethanol for vehicle fuel use here. But there are a number, in particular, the methane emissions from the headworks, sludge dewatering, sewer methane, and digested biosolids storage and dewatering that are in this updated inventory. Going to the next slide, well, I just highlighted the ones that we're going to talk about here today, which are the headworks and the dewatering. And these are the storage tanks. They're lighted with sodium halide lighting, which is why the photos are so yellow. But what you're seeing is the ductwork on the roof collects the foul air from the storage tanks so that we could measure at a point that currently has a flow meter there. That's where we put our FID instrument to measure it. And we only did about 4 hours of sampling in the winter and 4 hours of sampling in the summer, or at different flow rates. And what you're seeing here is that we had 2 different sets of data at 2 different digester feed flow rates, and we drew a straight line through it. Now, this is, what do you want to say? If you look at the methodologies for storage tank methane when we started this test, there's no methodology. So our bar that we were trying to exceed or do better than was, we know there's methane here. Can we measure enough that we can come up with a basis for a methodology that's a function of flow and how much flow is going through the digesters and coming out of the digesters? And so that's where we came up with the methodology and the curve that's there. The next slide shows what we did with sludge dewatering. And we ran the dewatering over a 4-hour period at different flow rates. And we ended up with something that looks like a reasonable correlation. And in particular, I'll call your attention, this particular straight line we forced through 0. And the idea being that if I'm not sending any digested biosolids to dewatering, I would expect to get 0 emissions. The rest of the information on the background, those are in the bottom left, are all the covers for the belt filter presses for final dewatering. And then if you look at the foul air control unit, we would basically insert our FID instrument into ductwork that was going into the scrubber. So that's where we collected these data. Now, the next thing I'm showing you are some curves that we did for DC Water's East Headworks. This is the larger, newer of the 2 headworks. It treats about 60% of the flow coming into the treatment plant. And I want to show you the axis on the left is how many grams of methane are being produced per day. And the numbers are relatively large from this headworks. The other headworks, which I'm showing you data here from the smaller, older headworks, that has a lot less air fed to the grit tanks, are a lot less. So I'm just going to flip back and forth, and you'll see that the magnitude of these curves, the orange line is for the most flow, the purple line is for the least flow, and then the temperature of the sewage was correlated here. And these were based on a sampling campaign that was at winter and summer temperatures. But again, looking at the magnitude of these curves, and it's per MGD and per temperature, when I look at these 2 curves, there's about 4 or 5 times more methane being released by the newer headworks per unit flow than there is with the older headworks. Anyway, going on to the next piece, this was some brainstorming that we did at a workshop in Toronto. And the question that we were asking here is, where do you think we might look for methane? From a solids handling standpoint, there were lots of possible solutions. Fermenters, floating cover digester lids, pressure regulating valves, lagoons, dewatering, composting, buried biogas piping, RNG upgrading processes, side stream treatment processes, sludge and biosolid storage, odor control. Now the next column has mostly liquid stream sources. And the first one is potable water reservoirs. So that's not even on the wastewater side. Septic tanks are not part of centralized treatment, and yet we know they produce methane. Talking about sewer overflows and the receiving water when we put COD into it, sewage collection systems, sewer pumping stations and vents, headworks, primary and secondary clarifiers, activated sludge tanks, in particular anaerobic selectors, but other places may be places where we're stripping methane out of solution, trickling filters, tertiary wetlands, and then COD discharges to receiving waters. And this was recently added under the IWA 2019 update. So I guess the takeaway here is, if you have any of these process units at your wastewater plant, which almost everybody has at least one of these, if not half of them, then you might want to do some testing to see how much methane your process units produce. Now, the final note here is on our greenhouse gas library project, and we've basically been abbreviating this greenhouse gas library. we're creating space here, and it's actually the Climate Registry who's owning and maintaining this database. But we would love for, if you've measured Scope 1 emissions from your plant, we'd love for you to upload what you measured, what your plant was doing at that time, some summaries as to what your plant is configured and what it tries to do, and then other information, process data, recommendations on how you'd improve your experimental plan next time, and contact information if people have questions. And when we get enough critical mass on, say, headworks methane or anaerobic selector methane, then we would turn a group of volunteers from our expert international panel onto it to try and develop a methodology that everybody else could use. So with that, the last note here basically just says, call me if you have Scope 1 data that you'd like to put in this library. And it also says, if you'd like to be part of our international greenhouse gas expert panel, call me as well. And we'll include anybody who wants to be in those calls that are expected to happen either 3 or 4 times a year. So with that, I'm going to hand it off to Adrian Romero with Jacobs.
Thank you, John. Appreciate that. Good afternoon, good day, everyone. My name is Adrian Romero with Jacobs Engineering. Today, I'll be talking about direct measurements of methane. I'll provide you with some context of what we're doing as an industry for direct measurements of methane at wastewater treatment plants, some concepts and definitions there, and also I'll walk you through some of the methodologies, approaches that we're using as an industry to monitor methane at our facilities, understanding that we're still developing in the field, bringing lessons learned from the oil and gas industry, from landfill, merging it also with the experience that we have monitoring odor control, right? It's air emissions, odor control, but now bringing that experience into the methane space and merging it with the new approaches that I'm going to be talking about. John shared very great information about past experiences using different methodologies, but also the different sources that we can have in our facilities. And so what we're going to present on the methods are how we can bring those to monitor the different sources and the plan as a whole. So with that, let me go and start talking about methane monitoring, and starting with what is the intention of monitoring. And we can split this into 2. First is we can talk about quantification, and on the other side, source identification. And they can work well together, right? Where we're focusing here in this webcast is talking about quantification and getting to that mass emission in terms of mass per time. And John talked about grams per day, or we talk about tons of CO2 equivalent per year. Here, mostly we're going to be talking about kilograms per hour, but at the end, it's mass per time. We also can quantify in terms of concentration, knowing that the concentration will need to have that airflow rate in order to come out with that mass emission. So let's keep moving here. Some definitions and differentiations about some of these concepts. Quantification methods for methane at our facilities. We can talk about the site level, the facility as a whole, and source level. The site level is going to help us determine as a facility how much we're emitting and then keep track of our progress in there. But we also need the source level in order to get to the granularity needed to develop a mitigation strategy for that. So we need both to be able to mitigate and then continue to make progress there. We also have quantification methods that can be continuous or intermittent. Continuous will help us to determine what are the seasonal variations, or if there are any variations in terms of with operational changes. John alluded to some of those in that DC water example as well. However, intermittent measurements, some of the methods that we have available, can support the prioritization of this of the mitigation strategy and the sources that we're going to get to. I want to also make a reference to the fact that some of the emissions that we find in our wastewater treatment plants can be continuous and it can be intermittent as well. So if we have an intermittent source, we would like to have a continuous, ideally, right? A continuous monitoring so we can capture those events as an example. And then we have those quantification methods in terms of concentration and mass flow rate that I already mentioned in the last slide. So what are the current approaches that we have? I'm going to be talking about some of these in the next slide in terms of what's tracer correlation, mass balance methods, and such. But we have the classification in terms of plant-wide or the site level and the process unit direct measurements when we're trying to target the source quantification, source level. And then we have the analytical approaches, the analytical techniques from optical remote sensing. Some of these approaches use optical remote sensing, local semiconductors as well. This is something that we have been implementing from the odor space as well. So now bringing the methane sensor in there, and then gas chromatography coupled or not with mass spectrometry to measure and monitor methane for that. So we'll go over some of these from the site level perspective. We'll talk about tracer correlation, reverse modeling, differential absorption LiDAR, continuous gas sensing, and drum flux method. And they all will have different outputs, but the goal is the same, right? Try to get to that mass emission rate of methane. Let's make sure I got this one. So starting with the tracer correlation, it's a plant level intermittent method. It is recognized as the most accurate of intermittent methods. It's based on a controlled release of a tracer gas nearby the source. The source can be the full facility, or it can be a tank or a vent. A known mass of a tracer gas, and then the monitoring of both the tracer gas, and the methane a certain distance, and use that ratio of the tracer gas with methane to determine the actual mass emission of methane. It's limited largely to academic practitioners because of what it's involved to do it. But again, as with anything, there is a technology or methodology development first in the academic area, and then we start implementing it in our practice. Masking or interference of other sources can be an issue with this method, but again, it's recognized as one of the most accurate for intermittent method. The reverse dispersion modeling. This is something that some vendors out there have implemented for odor control, monitoring odors of our facilities. It's a plant level, and it's based on concentration measurements. But then we bring our dispersion modeling experience to track all the way to where the source is of those measurements. But again, using it from the perspective of the plant as a whole first. We need a sensor that can monitor methane concentration, and then we combine that with methane data, weather data, some temperature pressure, so we can do that reverse modeling on that one. Moving to our next one, let me see. Yeah, differential absorption LiDAR here. It's a ground base or aerial. Ground base is the example that we have on the right with a truck or a vehicle that has equipment in it, or it can be aerial, it can be a helicopter or an aircraft. It's based on that method of having live reflection and then the scattering of it, and then bringing back that signal so we can detect and quantify how much methane is there. It's recognized as a high quality method there. It does require an articulated vehicle. That means that we can move around the plant and determine the mass emission rate for methane for the site level perspective. It can also get into some of the different sources, limited by the fact of physical limitations of getting to the source with the vehicle as well. Then we have the unmanned aerial vehicles, the drum trucks wall. Chung is going to be talking a little bit on this in his example in a few minutes. It's intermittent, and it can support source level as well. This is great for site level, but also can support source level. And basically, this is a drone that has already the sensors, methane and weather sensors, air velocity, air direction, and then goes around and creates this wall of the different fluxes in terms of methane, and create that cool graphic there to then get the overall site level concentrations. Drone can also move through different sources, so that's an advantage for that. And some of the limitations is that we cannot fly drones everywhere, right? If there's an airport nearby, there might be some limitations to implement this method. Continuous gas sensing LiDAR, similar to what I spoke before. However, it's a different technology based on laser. It combines tunable diode laser with differential absorption, lidar, and photon counting, just to sound fancy. It looks very fancy, sounds fancy. It's very accurate. It's commercially available, and it allows to have that side level. If we have a couple of options, they're also mounting it in a vehicle or putting it on a mast, mounting it on a mast, and then have up to 200 meters radio that we can have that scanning of methane emissions. It's impacted by wind, like most of the methods that we're talking here, and it continues to be challenging when it comes to fugitive emissions in there. If we have that 360 that I was mentioning, it's can be, again, continuous, non-continuous. It depends on the rate of scanning that we have. Again, another method available for site level. Another site level that it's coming up, right? We're learning more how to implement it. It has there are great examples that already have been implemented for major sources. And this is satellites, using satellite image to then determine methane emissions. It's again great for site levels, and it's relying on that accuracy of the quantification. Right now, some of the satellites and algorithms that are available can get to around 100 kilograms per hour, which is above most facilities, but there are some facilities out there. So it will be great for site level. If we want to get to the source level, that will be more challenging. However, there is some work out there with some artificial intelligence also pushing to get to a lower detection limit. So it would be great to have that capability in the near future. Moving to the source level here, we have optical gas emissions on cameras, and basically using the thermal camera technology to detect and quantify. Some cameras can quantify, not all of them, but there are some cameras overall that can help us detect methane and help us see what are the main sources. And then we can use that quantification capability that some of them have. An advantage is that we can do some sources that are difficult or unsafe to reach, and be able to have that quantification of that. Then our last one here in terms of source level is the flux chamber, something that we have been using in odor control for a long time for aeration basins, tanks, any area source will be use a flux chamber for this. Advantages that we can use other gas, we can measure other gases such as N2O, and it does rely on that analyzer in the back end. The flux chamber is going to help us control the emissions that are coming, have a good understanding of that airflow, but then we need to still monitor and measure methane. So it's going to rely on that sensor or analyzer that we're going to have in the back end. So starting to bring it all together so we have enough time for trying to talk some examples on application of some of these methods, is that we can start looking at these methods from the spatial scale and the temporal scale. Spatial scale is when we start talking about the top-down approaches or the bottom-up. Top-down, talking about satellites moving down all the way to aircraft sampling, some of the towers that have some of the sensors that I talked installed, and then moving to the vehicles that have been implemented there, mounting the equipment, driving around the facility, all the way to individual sources using direct measurements of methane from the source. And also, as I mentioned before, continuous versus intermittent measurements. Key considerations, there are some standard methods there for some of these approaches that have been developed mainly for the oil and gas industry and trying to bring them into our industry as well. They're still not specific for water resource recovery facilities. There are specific guidelines. Some work is being done in the UK, some work is being done in North America. John mentioned some of those projects that are moving towards that. So we continue to work that as an industry. There is some another key consideration here is that, as I mentioned, most of these methods are impacted by wind and weather characteristics. Some of them are going to be more impacted than others. And again, background concentration, some other conditions can affect this monitoring. My last slide is that some of these solutions are remain large improvement for water resource recovery facilities. So we continue to implement it, we continue to learn, and start getting the ones that are working better, again, understanding that site-specific conditions play a role. Site-level measurements can provide very accurate picture of the emissions as a whole, but they're not that accurate in the source level quantification. And the opposite is true for the source level measurements. So you can start thinking already that if I want you to get something out of these 15 minutes that I spoke, is this last bullet point, that we have all these tools in our toolbox right now that we continue to implement and transfer to our industry. But so far, and it's the same for the other industry, it's multiple methods are required. So there is not a single method right now that can give us both the plan-wide and the source level quantification that we need. And with that, I'll hand it over to Trump so he can talk to us some examples. Thank you.
Thank you, Adrian. So Adrian and John really gave some good context to what we're going to talk about next, which is a case study in which the city of Columbus used and performed the first multi-sensor fugitive methane campaign in the Western Hemisphere on the commercial scale. So the city of Columbus, they have two treatment plants. The one treatment plant that we're focused on is the Southerly Wastewater Treatment Plant. It's about 300 acres, average of about 115 MGD of average flow and a 440 peak flow. They have a two-stage digestion system with a Class B liquid and cake end-use program. And what you see to the right is the layout of their facility, and the bottom is the solids treatment process system. They have acid phase digesters and methane phase digesters where their biogas is sent to flares. They're currently not used in the boilers due to the quality of the biogas. The digestate system is split into the thickening centrifuges and the dewatering centrifuges, in which they have a liquid storage tank that has storage capabilities up to 6 to 9 months before they liquid land apply, and biosolids cake storage for about 2 to 3 days before it's land applied from there. So their program currently is in a state in which they are looking to expand to a new program. And that new program was partly predicated on their climate action plan. They were looking, like many other facilities, to meet their climate action goals. They had a goal of essentially reaching a 45% reduction by 2030, about 100% reduction by 2050. And thinking about that goal as well as kind of the needs of the program, they wanted to initiate a new bioenergy program. And that bioenergy program was in part looking to increase digestion capacity. It was looking to beneficially use biogas at their site through co-digestion. And then it was to initiate a co-digestion program in which they could then produce more biogas to produce electricity to reduce their scope 2 emissions. One of the neat things about that project was that IRA funding was available, and it's something that we walked them through. And it's actually, bids are supposed to be coming out pretty soon, in which up to 50% of the program was going to be covered through direct pay. And understanding their current climate action plan, one of the things that we had seen during planning, and this was actually some stuff that John Willis had worked on, was that there was some indications for some major fugitive methane emissions that they didn't think would align with their climate action plan, as well as their goal to beneficially use biogas. One of those indications is shown here to the left. Essentially, the figure to the bottom shows blue as the solids, the thickened sludge going into their liquid land application tanks. And then the orange is what's going out. So what they were seeing was potentially residual digestion occurring over that 6 to 9 month period, and roughly about 26 to 30% additional VSR. If we assumed, we weren't certain at the time whether it was anaerobic or aerobic conditions. If you assumed all that was anaerobic, roughly about 105 kilograms of methane per hour would have been emitted from their liquid storage tanks. And that would essentially have doubled their emissions from their scope 2 energy use. The other kind of parameter at the plant that they were seeing during planning stage was that they have 6 digesters. 5 of the digesters had floating covers. And as many of you guys know, floating covers are potential sources of methane leaks. They also had one fixed cover. And what they saw was essentially there was a 20% to 30% differential between the biogas meters between the two systems. And we're seeing that potentially leak out of the system from the covers. It was estimated roughly about 112 kilograms of methane per hour would have been leaking from the floating covers again, roughly doubling the scope 2 emissions at their plant from their electricity use. So based on those considerations, and again, to align with their bioenergy program goals and their climate action plan, the city reached out to ask to help essentially develop a fugitive methane campaign to understand where the emissions were coming from, and then to establish a mitigation program. So one of the first things we had to do was look at all their potential sources. Many of these, were covered by either John or Adrian, but some unique factors of the plant was they have that big liquid storage program. A lot of that headspace air is actually sent to a series of odor control units. All the thickening and dewatering process air goes to a bunch of biofilters. They have that cake loading out facility. They have a lot of different appurtenances at the facility that were reaching kind of older stages of life. And of course, the floating cover, as you can see in the bottom right, was a big potential source of leaks based on the video and the feed that we could see of the bubbling of the gas, the solids there. So kind of keeping all those factors in mind, we had to develop a measurement campaign. Adrian covered it broadly. It was really a composite of the two frameworks, the bottom-up framework and the top-down. Bottom-up really gives a different type of level of assessment. Essentially, you're looking at each individual source emission, and you're essentially trying to get a quantification for individual components. The challenge with that is it has great localization of emission sources. Really not the best quantification because you often miss sources of emissions, especially if the detection limits are for the equipment that you use are a bit higher than the emission sources. So the way we approached that is we used optical gas imaging that Adrian mentioned earlier. We're going to talk a little bit more in detail about that in a second, but we use OGI to do source and leak detection. It's really the bread and butter of leak detection within the oil and gas industry. Along with that, we used FIDs and different kind of discrete sampling methods along that to really check our top-down method. So top-down methods have a bit different spatial and temporal scale. The method we use is this flux wall method that Adrian has spoken about a little bit by this company called Explicit. And the really great thing about top-down methods is they generally are much more accurate on quantification, but they can struggle on the localization of the source emissions from the site. So just get a little bit more into OGI. It is a really sensitive IR type of technology. It's really image spectrometer is what it is. And essentially, every greenhouse gas essentially has a different type of fingerprint. And that fingerprint really changes, every greenhouse gas has a unique fingerprint on the infrared scale. So as background radiation goes through a greenhouse gas, it changes the energy from that and adapts it to the scale or the bandwidth that is localized on the IR spectrum. So these type of cameras are unique because they have the ability to just screen that really discrete level of bandwidth, and what was once invisible can then be visualized through a thermographic image through OGI, and you can kind of see that to the bottom left. So drone flux, Adrian covered a lot of this. I'm going to shorten this, but just saying that it is kind of interesting because it's not dependent on dispersion models. So the technology itself allows you to run these vertical flux walls in which you sample roughly several hundred points. It gives you good detail on the plume distribution and the plume profile, providing a great means to do mass emissions quantification. It is a mass balance method, so you do identify an area and you run scans upwind of the plume and then downwind the plume and deduct the two. So we're going to run through actually some of the results from the surveys that we were doing. This is only a couple of the surveys data due to time restrictions we have, but what you can see here is dewatering. It's been known that dewatering is a source of emissions, especially some of the work that John has done in the past. What you see here is on the top is the visual image and the bottom is the thermographic image. And the clustering of different white colors that look like plumes essentially is the methane plume. This is from the dewatering chute. The black is the liquid storage tank. All that air from the headspace is sent to the biofilters. I know there's a question about whether biofilters do any biological oxidation, and we can actually answer that question in the chat. But essentially for Columbus, it didn't really do much for methane reduction. What you see in the third image here is the cake loadout facility. As the cake was loading onto the truck, emissions was distributed out of the tank, out of the trucks, and then out of the vent shown there. And then lastly, digestion PRVs. Digestion PRVs are quite a common leak source. We're not going to cover it in depth today, but many issues that result from the design of the pressure set point for digesters, PRVs, and then the operating pressure leads to more continuous emissions than you would expect from those type of safety devices. Some other results that we saw, I mentioned the floating covers. Those were one of the primary leak source. What you see here is kind of the emissions from the annular space. Columbus doesn't mix their digester continuously, and they don't feed each of the digesters at the same time. So what you're seeing is kind of this irregularity or intermittence of emissions, like Adrian had mentioned. So it's kind of interesting to see that. One last kind of image here that I want to show was this digester tank. The structural engineers had come out a couple weeks prior and had evaluated the wall for structural integrity. The kind of really unique thing about OGI, and there's many other applications of OGI beyond leak detection, is that we saw here is a crack that wasn't visible to the eye. It was an indication of emissions out of the wall, indicating particularly a more foundational crack in the digester. And there's a air handling unit right next to it that's an exhaust fan. The city of Columbus, immediately placed that as an issue of concern, and they moved that air fan to the wrist. This was really unique for OGI's application because it's a really strong visceral image. And the city of Columbus actually invited the local EPA out, and you're seeing here the staff on site looking at the data we're seeing live through the footage that we were conducting. So kind of really interesting material. We did do quantification as part of it, but its primary purpose here was to identify leaks so that we can develop really good granularity on the locations of emissions for mitigation purposes. What you see here now is the results of the drone flux method. This is an image of the flux walls. It was roughly about 50 kilograms per hour. So one of the larger sources of emissions was a combination of the digesters and the BLAF. The digesters on this kind of video or footage is shown to the left, and the BLAFs are the four rectangular tanks there. But one of the kind of interesting things that we're seeing that is also a challenge in many other industry is reconciliation of different data sources. So what we saw here was about 50 kilograms per hour. And I want to note that the drone method, like Adrian mentioned, it's an intermittent type of sampling method. This is a snapshot in time. So there's a question about how often do you need to run drone flux to do really good quantification or representative quantification of the year. That's still science that's being in development, but we have generally a good idea of when to run it. Typically, summer, winter operations tend to be representative of the year. Relative to what the data was shown prior, it was only about 20% of the flow meter data for the digesters, and about 25% of the VSR estimate for the BLAF on the residual digestion. I think one of the things that was clear from that was that perhaps not all the anaerobic conditions were there for digestion within the BLAF. We also ran a waste gas burner efficiency test here. This was kind of interesting because the efficiency of the waste gas burner was actually really good, about only a 0.5% slippage on the waste gas burner. The EPA has a general default about 1%. I think one of the reasons why the waste gas burner performed so well was because it was essentially flaring all the gas at the plant. So it was a pretty continuous amount of gas flow to the flare. And then this is lastly the biosolids handling facility. So this is where all the dewatering and post-digestion thickening systems are. This area also includes gravity thickening and the dewater cake storage. Like mentioned prior, we didn't have good localization of actual emissions, but we could tell from the area that was the total composite. It was roughly about 18 kilograms of methane per hour. So it was unexpected in the fact that it was higher than we had anticipated. But it was good because this really allowed us to develop solutions later for mitigation. I mentioned other methods. We did do that discrete sampling. They were in the ballpark. We had not intended them to be the primary source of quantification for this type of campaign, primarily due to the cost of labor associated with it. And there was some sampling bias due to the access and available areas that we can sample, but we're showing some of the FID work on the odor control. We did some general bag mass flux methods there as well. So in general, the outcomes showed roughly about 70 kilograms of methane per hour, roughly about 18,000 metric tons of CO2 equivalent per year. You kind of see the breakdown here from the different areas. Most of the emissions came from the digesters and the BLAF, and then roughly a little less than a third came from the solids handling areas. So what I want to kind of show here at the end sorry, we actually have a couple more slides. What I want to show here was this figure is kind of really interesting because Columbus was moving towards a bioenergy program predicated around co-generation, co-digestion. And this figure essentially shows greenhouse gas reduction and methane leakage. And I think for this, you can just focus on the X axis here. What is shown is different electricity production based on the source of fuel. So you have coal, oil, and natural gas. And where we're at with the campaign was roughly about 15% of the biogas production was being emitted or leaked from the site. So what roughly it was equivalent to oil. And this was something that, was not something the city of Columbus desired or wanted at all. But there is a bit of a reality here. What you see also is the plant data represented about 40% of the total biogas production. And what we think it really is it's between 15 and 40%. And really any number for the city of Columbus is not something they wanted to have. I'm not going to jump into depth on this because there's other calls later that are going to cover some of this. This really gave a great baseline for us to understand their greenhouse gas emissions, the localization, kind of the granularity and the potential changes. We performed a really comprehensive mitigation analysis that investigated all the different locations and areas that we could mitigate emissions and look at a universe of different technologies out there as well as methods and means. And the really great thing about it is we were able to get to a bunch of solutions that allowed the city of Columbus to roll it into their bioenergy program as we were designing the program. So this slide is showing the baseline of 2013, and by 2050, it's shifting to a significant reduction through all the different solutions that are implemented, roughly about 80% reduction in scope 1 and 2 emissions. This does include the utility moving towards net zero. It does not include N2O. That's the next project that we're working on with them. But it was really great because a lot of the quantification and measurement efforts led to feasible mitigation solutions for the city of Columbus. So I do want to end here with one concept because I think Adrian covered it and John covered it. This is an evolving science. David Ponder often tells me this, is don't let perfection get in the way of progress. There is a lot of really great methods and means out there. Even the oil and gas sector has not gotten to the point where they're super confident in the means and the methods for for quantification quite yet. It does require a composite of bottom-up and top-down solutions to get you the level of detail that you need. And even if you're not looking to do high levels of quantification with high accuracy, things like OGI or discrete sampling or using even a sniffer to investigate your site is a really important thing to do that could be done now to reduce methane emissions. So that was the end of my talk.
Thank you so much, Trung. So everybody, I guess, come back and screen. There we go. And so you can stop sharing your slide, Trung, so that everyone's on. We have a lot of questions, but then we have 7 minutes. So we're going to do our best to choose maybe one or two. And so there's a specific question here for Adrian. It says, my organization uses drones to measure methane emissions from a landfill. Could something, give me a second. So I think the question is about, exactly how do you use your drones, basically? It says, could something like this be used at a wastewater recovery facility? And it would seem applicable. So basically asking, can you use drones? Because I know you mentioned something around that.
Thank you, Jessica. Yeah, I would like to say yes right away, but of course it's a type of drone that is being used, a type of method, and the intent again, right? You're trying to go for detection, you're trying to go to do quantification. Trung showed the example as well of drone being used with the flux wall method. So if it is something like that is being used, definitely. But yeah, thank you, Ahmed, for the question. So it'll be depending on that methodology is being used with the drone. Sounds like it.
Yeah,
Right.
I will.
Thanks, Adrian.
Sorry, I'll just add a little comment
Trung.
on that. There are many different drone methods out there. Landfills tend to move towards surface emissions monitoring. I think the things that we've seen here in the industry, and Adrian kind of covered it, is there is an adaptation period. Wastewater treatment plants are quite unique in their geometry and their systems and their emission sources relative to an oil and gas facility or to a landfill. So I just want to add that comment. It probably takes a little bit of time to adapt it and get it to be applicable.
All right, thank you. And so I'm guessing I'll direct this to John if you can. It says, have you any data on methane being removed, destroyed, transferred elsewhere in odor control systems? For example, wet scrubbers or carbon scrubbers?
Well, so typically, I mean, a wet scrubber can dissolve some methane in the water, but it's a pretty insoluble gas. So we wouldn't expect much removal there. They've seen some removal in biofilters, but if you think about it, if you're feeding methane to the biofilter all the time, there's a good chance you're going to contribute to the growth of methanotrophs that consume methane. But the data that we've seen says that a biofilter needs to be sized for detention times that are on the order of 5 to 10 times more than we normally design them for our industry. So, and who knows how much methane reduction you're going to get then. They're not very effective. As far as we know, there are no very effective methods to biologically reduce methane emissions using odor control.
Thank you, John. Anybody else have anything to add? Okay.
I can
Next
add that, sorry.
Oh, go ahead, John.
Like John said, because he reviewed some of this, we did do a deep dive. Landfills are trying to do this with different type of caps and biofilters, but like John said, it's 5 to 10. It can be up to 50 times because the methane oxidation pathway is much slower than for odorous compounds. There are some companies out there trying to explore it more, but it's not ready yet. And yeah, biological pathways currently aren't really assured to remove methane.
All right, thank you. And I think this is a really interesting question. 4 minutes left, my eyes are on the clock. But it says, for a specific site, how do methane results from plant-wide and process-wide specific methods compare and how the discrepancy? So I think, Trung, you spoke a little bit about that, but anybody can feel free to answer.
Yeah, so there it is a challenge. There's some guidance in oil and gas guidance document called OPMG 2.0 that provides some guidance on it. There's some statistical analysis you can do. I think it's a little bit of, top-down methods are not always the most accurate, and the temporal scale is not always there. In cases that John had showed earlier, when you have a lot of the emissions going to odor control duct, and the fan speed and the amount of air coming in, and the concentration, you're likely going to get the most accurate information from there. It's a bit of working through kind of the data sources and the uncertainties that and looking at kind of the statistical elements of the data, like deviations, to understand what is the best kind of quantification data there, and then compiling it. It is not easy. I'll say it is not easy at all.
Well, and I would say almost the other way. If you put 2 flow meters on the same sludge pipeline, all you do is ensure you're going to get 2 different values. And this is exactly that same sort of way. When we were doing the Columbus work that Trung's talking about, we would do 3 different methodologies. We had different levels of confidence in them. But what we saw is one method said it's 112 kilograms an hour. Another method said it's 36 kilograms an hour. And the last one said 20 kilograms an hour. And those are 3 completely different numbers. So what we're trying to do as an industry is figure out which is a better method. I mean, the other thing for example, and somebody was asking, can you use drones and how effective they are? The challenge with a drone is when it's in the air doing a flux wall, it takes 45 minutes, but it's only for that 45 minutes. If you're running it for nitrous oxide, plants have seen that 80% of the nitrous oxide might evolve in 1 hour a day at a peak organic loading rate. And if your drone isn't in the air at that time, it's going to assume you got 0. So this science really is in its infancy. And we as an industry, and there are projects, and WRF is working on this, we need to figure out what it means. So if you are interested in getting involved in some of that, you can call either Trung, Adrian, or I. We're on similar teams working on these projects, and we'd love to have anybody who's interested look over our shoulders as well as be a first-hand contributor as a site to measure. So give us a holler. Yeah,
thank you. And so last question before I hand over to Jeff is someone is asking that can Trong, and I guess maybe John, if you can, share the methane mitigation strategies that were considered by Columbus. They want to get an idea of how to mitigate.
Yeah. We had spent a lot of time pulling together research data, reaching out to a ton of different vendors, talking to all the odor control people, talking to all the, because I know there's a comment there about thermal oxidizers. Thermal oxidizers are a pretty common source to reduce methane emissions, particularly in foul air. There was a lot of effort that went into it. We looked at vacuum extraction. There's many different means and ways that we can ask City of Columbus if they're willing to share that document with that individual.
Well, and let me tell you, there's
helpful.
another place to look. If you look at this month's version of WENT, there's an article there that talks about the Columbus testing and what we ended up with for mitigations methods. So it's there. You can read it. It's in the public domain. Tear it up, and if you got questions, give us a call there too.
Yeah, and last thing on that, Jessica, is that we will have another, we have the N2O emissions webcast, and then we have another webcast on mitigation strategy as well. So
that's right. Thanks, Adrian.
Thank you. That's a very good reminder. And so I just want to say thank you to John, Adrian, and Trong. And so that was a very informative session, too short in my opinion, but thank you for today. And so Jeff, if you can come on screen and we can close off.
All right. Well, thank you, Jessica. This concludes our webcast today. Thank you all for participating. And in addition to thank you to our speakers, and thank you also to our moderator, Jessica Conde. Really appreciate it. We hope everyone will be able to join for parts 3 and 4 of this webcast series later this fall. And until then, thank you and have a great day.
Thanks, Jeff and Jessica.
Thank you,
Take care.
Thank you. Bye, everyone.